Alrighty, welcome back. So now we're going to talk about applications, or in other words, how to use logic gates to actually do things, right? We defined all these gates, and now we want to actually sort of tackle some kind of problem that involves using these gates. Alright, so let's look at a first problem. So for the first problem, let's build a switch. Okay, so what is a switch? So consider the following situation. Here's me over on this side, and here's me with my cell phone. Well, my landline phone, I should say. And I have two friends. One of my friends is named Alice, and one of my friends is named Bob. And I sometimes want to talk to Alice, and I sometimes want to talk to Bob on the phone. But I never want to talk to Alice and Bob at the same time, because then they'll talk over each other, and I won't be able to understand what they're saying. Okay? I mean, if you have a phone line coming out of your house, you want to be able to choose who you're talking to at any given time. And so you do this using a circuit, which is called a switch. Okay, now in reality, all of this is going to be a lot more complicated, but pretend we're in this simplistic scenario. So the way this should work, Alice should be sort of transmitting a bunch of data to you, just the data of what she's saying. And Bob should be also transmitting a bunch of data to you, and this is just the data of what he's saying. And you want to choose which one that you're listening to at any given time, and so you use what's called a switch wire. So you can think of this as a circuit with three inputs. So this is the first input, this is the second input, and this is the third input, and this is the output. So maybe this is a one-way telephone. But the point is that there are three things coming in. There's Alice's voice, there's Bob's voice, and then there's the switch wire. And the way this should work is that if I put in a 0 on this switch wire, then I should be listening to Alice, right? So if the wire is off, then I'll be hearing whatever Alice is saying. But on the other hand, if the switch wire is a 1, or in other words, if it's on, if it's charged, then I should be listening to whatever Bob is saying. Okay, so there's two possibilities. I'm either listening to Alice or I'm listening to Bob, and this only depends on what I give this switch wire. So Alice and Bob are in control of their telephones, but I'm in control of the switch wire and my phone, so I can choose who I'm talking to. Okay. So you might ask, what does this have to do with logic gates? Well, you can think about you can think about it in the following way. So Alice is speaking to you over a phone, but you can pretend that this is actually happening digitally, which means that everything she's saying is being encoded somehow into ones and zeros and being sent in sequence through this wire. So Alice is basically charging her wire and then decharging her wire and doing this over and over again in some pattern which the computer, or which the phone line knows how to decode and encode into a sound, into a voice. And Bob's is doing the exact same thing. So there's ones and zeros coming from this wire, there's ones and zeros coming from this wire, and there's ones and zeros coming from this wire. And it's outputting ones and zeros, which then get reconstructed back into whatever voice I want to actually hear. So in other words, this should be able to, you should be able to do this using logic gates. And to make this even more clear, let's look at the truth table corresponding to this situation. So in this situation, there's three inputs, right? A, which stands for Alice, B, which stands for Bob, and S, which stands for switch wire. So Alice will be this first column, Bob the second, and switch the third. Okay, so let's say the switch wire is on 0, and Alice and Bob are both transmitting zeros. What should happen? Well, the switch wire on 0 means that I should be listening to Alice. But Alice is saying 0. So the output is 0, so I hear a 0. Okay, so the same thing applies for all of these, so maybe we'll look at this fourth one. So if the switch wire is a 1, that means that I'm listening to Bob. So what's Bob saying? Well, Bob is sending me a 1. So the output is a 1. Right? Similarly, if let's say I'm here in this second to last column, the switch wire is on 0, which means that I'm listening to Alice again. And Alice is saying 1, so I hear a 1. Okay. So at this point, I would encourage you to pause the video, look at this table, and convince yourself that this really is the truth table corresponding to the situation. Right? If this switch wire is a 0, then I should hear whatever's happening in this first digit. And if the switch wire is a 1, I should hear whatever's happening in this second digit. Okay, so take some time to think about that. Okay, so now that we know that, I mean, really this situation is just governed by some truth table, you should in principle be able to construct a circuit realizing this truth table. So why don't we think about how to do that? Okay, so now we'll go to the actual building of this switch. Okay, so I've now set up a bunch of circuitry, and I'd like to explain how this actually works and what I'm trying to do. So Alice has her input here, Bob has his input here, and for the moment we're just going to assume that Alice is sending a 1 and Bob is sending a 0. So this top wire is going to be yellow, which signifies that it's on, and the bottom one is white. Hopefully you can see this. Gray means that something bad is happening, and in this case something bad is happening because I haven't given anything to this port in the AND gate. Okay, and lastly there's a switch in the middle, which corresponds to the switch wire. Now, I'm doing a funny thing here. I'm taking Alice's input and I'm putting it into an AND gate. And I'm taking Bob's input and I'm putting it into a different AND gate. So you might ask why I'm doing this, right? So I want only one of these messages to go through at one time. Now, Alice is sending some data into this AND gate, right? It could be a 1 in this case, or it could be a 0 if she's, sending a 0. But what happens with an AND gate, right? If you look at the second port, if I put a 0 into the second terminal, then this AND gate always outputs 0, right? An AND gate, if I put a 0 here, then no matter what this top portal is, input port is, it's always going to spit out a 0. Okay. But on the other hand, if I put a 1 into the second terminal, then this AND gate is going to output whatever Alice is saying. So if I put a 1 here, if Alice is saying 0, then I have 0 and 1, and I output a 0, which is what Alice was saying. And if she sticks in a 1, then I have a 1 and a 1, and I output a 1. Okay. Now everything that I've said for Alice works the exact same way for Bob. Right, so in this example, if I feed in this example, no matter what, if I feed a 0 into here or a 1 into here, I spit out a 0. But the point is that if I put a 0 into this wire, then no matter what Bob is saying, this will always output 0. But if I put a 1 into here, then this AND gate essentially routes Bob's message straight through. So this is kind of convenient because now I've given you a way to turn on and turn off Alice's message and turn on and turn off Bob's message. And this should be governed by this switch. Right, so how do we do this? Well, the point is that this switch, if it's off, then I should hear Alice. So if this switch is off and is sending a 0 out, then there should be a 1 going into here. And similarly, if there's a 0 going out of here, there should be a 0 going into here, into Bob's AND gate. And vice versa. So in Alice's gate, what I can do is I can take this signal coming out of the switch and I can put it through a NOT gate, and then I can put it into here, right? So what's happening? Well, the switch is 0, which means that I'm now listening to whatever Alice is saying. And that's what is happening here because there's a 1 going into this AND gate. And if you look at the result of this circuit, the light bulb turns on, which means that we've read a 1. Similarly, I can do the same thing for Bob's gates, but I want to do the opposite of what's happening for Alice's gate because I only want to hear one of them speak at a time. So now I just take the switch wire and I direct it directly into Bob's AND gate. Okay. Now this OR gate is just something I need to put at the end because, I know that only one of these is going to be on at any given time, right? If the switch is in Alice's favor, then this one might be on. If the switch is in Bob's favor, then this one might be on. But they're not both going to happen. But so I just take the outputs of these things, feed it into an OR gate, and then I spit out the output. Okay, so if the switch is on, then I'm listening to Alice, off, then I'm listening to Alice, and I get a 1. And if the switch is on, then I'm listening to Bob, and if you look at what happens with Bob's message, it goes all the way through and you get a 0, so this light bulb turns off. Okay, so this is what's happening with this switch circuit, and this is, specifically this is how you build a switch circuit. I mean, I wanted something that lets me either listen to Alice or Bob, and with just using 4 simple gates, right? So 1 NOT gate, 2 AND gates, and 1 OR gate, I can make this happen. So this is one application of the logic gates that I introduced in the last 2 videos. So now let's move on to a harder example. Okay, suppose I want a circuit which takes 3 inputs and outputs 1 if exactly 1 input wire is on and 0 otherwise. Right? So, there's 3 input wires going in, and I want to sort of detect whenever only one of them is on. Okay, so if you look at a picture, there's some mysterious circuit that should be doing this for me. And if I give it 2 ones, this is just an example, and a 0, then it spits out a 0 because it's not true that exactly 1 input wire is on. In fact, in this case, 2 input wires are on. So this is bad, and the circuit says no. Okay, but on the other hand, if I turn off the second wire and I just have the first wire on, now we're in exactly the case, for my specifications where this circuit spits out a 1. So 1, 0, 0 corresponds to a 1. Okay. So this is a slightly harder example. I have 3 inputs and I want to do something slightly more complicated than just switching from, Alice to Bob, or 2 of these wires coming in. Okay, so let's do this. So how do we do this? The first step, like in the situation where we wanted to build an OR gate out of an AND gate and a NOT gate, is to draw a truth table. Right, so let's draw the truth table corresponding to this situation. So there's 3 wires coming in. I'll call them, let's say, A and B and C. And if you just look at this truth table, it reflects exactly the situation that I described in this text over here. So if there's 3 zeros, then I get a 0 because it's not true that exactly 1 input wire is on. Okay. In the second case, exactly 1 of the input wires is on, so I get a 1. In the third case, the exact same thing is true. Right? The second wire is on and the other 2 are off. Wire B is on, so I get a 1. Okay, so maybe take some time on your own and go through the rest of this table and just make sure that this truth table exactly corresponds to the situation that I've described on the left-hand side. Okay, so I'd encourage you to pause the video, take a look at it, make sure that you understand what the circuit is supposed to do and why this truth table reflects what the circuit is supposed to do. Okay, so let's move on. So now let's actually try to build this thing. Now, first of all, before we try to build it, we have to sort of analyze what the strategy is going to be. So if you look at, for the moment, let's just ignore the bottom part of this truth table, and let's take a look at the top part of this truth table. So the first thing we notice is that there's 4 zeros here. So we can sort of ignore what's happening here because nothing's changing. And we can just focus on wires B and C and the output wire. So if you look at this truth table and just ignore everything that I put in gray for the moment, this table looks exactly like an exclusive OR. Right? 0, 0 goes to 0, 0, 1, and 1, 0 go to 1, and 1, 1 also goes to 0. Okay. So if wire A is a 0, then I want to take wires B and C and apply an exclusive OR. Now I can do the similar thing below, right? So I can just focus on the bottom 4. And what this tells me is that if wire A is 1, right, if it's on, then I want to do whatever corresponds to taking these 4 inputs to 1, 0, 0, and 0. But if you recall, this is exactly what a NOR gate is supposed to do, right? So I didn't actually define this, I left this as an exercise. But a NOR gate is essentially an OR gate followed by a NOT gate. And if you remember, an OR gate would give you 0, 1, 1, 1. So if we flip them by applying a NOT gate at the end, I get 1, 0, 0, 0. So this is kind of nice, right? I've told you that now this situation is either a situation in which I want to use an XOR gate, or it's a situation in which I want to use a NOR gate. And that depends on whether A is a 0 or whether A is a 1. So this may look familiar, right? In the previous example, I wanted to tell you whether I wanted to read from Alice's input or Bob's input, depending on whether this was a 0, some switch wire was a 0 or a 1. So in this case, it looks like I should be able to implement this by using an XOR gate, a NOR gate, and the switch that I defined earlier. And it turns out that you can actually do this. So let's take a closer look at the circuitry that lets you do this. Okay, so I've copied the truth table here just in case you want to take a look. Okay, I'm calling this the exactly 1-1 circuit because it only turns on when there's exactly 1-1. Now, if you look at the circuit that I've started building, right, I have the input B and I have the input C. And these are going to a gate here and a gate here, right? They're both going into each of these gates. So this one, if you recall, this symbol notation is an XOR, and this one is a NOR gate, just like we said in the previous slide. Okay, so we want to take the output of B and C, and then we either want to look at the output of this XOR gate, or we want to look at the output of this NOR gate, but that depends on whether A is 0 or whether A is 1. Right, so I want to take this basic circuit, and I want to tack on basically a switch gate, a big switch gate onto this side. And I've done that here. So if you recall, the switch gate corresponds to taking one NOT gate, two AND gates, and one OR gate. And I'm doing exactly that, except the inputs, instead of just being the raw input from the beginning, are now what you get when you take an XOR of B and C on the top, and what happens when you take a NOR of B and C on the bottom. Okay. Right, so really I'm just sort of attaching this XOR and this NOR gate to the switch gate that I defined before. And this makes sense because I'm choosing what happens based on whatever is happening with A, as in this truth table. Okay. Right, so there's a NOT gate here because when A is 0, I want to look at the XOR, and when A is 1, I want to look at the NOR, so there's no NOT gate on this wire. Okay, so if this went a little bit quickly, I would encourage you to pause the video, maybe rewatch this part again, and just sort of, maybe if you want, trace through this and put different inputs into B, A, and C, draw this on a piece of paper and try to figure out, or try to convince yourself rather that this circuit actually does this truth table. So let me just show you two more examples of this. So, okay, if B is on and A is off and C is off, then I should get a 1, and I get a 1. If I turn A on, then suddenly I've changed the situation to where I have two 1s, which is not exactly 1-1, and so suddenly this light turns off, which is what we wanted. And lastly, if I turn off B, and if I turn off A, and if I turn on C, then this is the situation that we wanted, and so this light turns on. Okay. Great, so now, again, it's your turn. So there are a bunch of exercises that I'm going to put after this, and they're all more applications of things. So Christina has made some nice, a nice application of these logic gates to doing encryption schemes, so I would encourage you to take a look at that one, and I've included some extra other ones if you want to, get some extra practice with these things.